Hello there. In this video, I cover the topic of control flows. I'll save the topic of functions for a separate video. The learning outcomes for the whole week are to create control flows in R, and we'll explain what we mean by control flows. To understand the concept and benefit of vectorization, and again, this is a concept we'll need to explain. To call functions in R with specified arguments, and to create our own new custom R functions. And so here maybe this is where some people might say we start to do actual coding because we start to program and create our own functions using all sorts of control flows such as for loop and while loop. But I don't want to get ahead of myself. I'll start with the first slide. Now there's also a last point, which is to use the help menu in R, RStudio. There's a few slides about this. Okay, for now, the concept of control flow. So here I put a quote from Code Academy. So it's called Code Academy. They must know something about coding. Control flow refers to the order in which statements and instructions are executed in a program. It determines how the program progresses from one instruction to another based on certain conditions and logic. Now, this sounds a bit maybe abstract. In general, when we talk of control flow, we simply mean that a computer program can have many steps, and it's not always the case that it should execute just in order all those steps. It can be that some steps need to be executed only if certain conditions are verified. Maybe some of the steps needs to be executed many times. So the general organization of the code blocks is what we refer to as control flows. And here we present some sort of fundamental statements that help us build our control flow. There's the if statement that is used to, well, simply execute something if a certain condition is satisfied. If the condition is not satisfied, well, a given block of code will not be executed. And then we have the notion of loop. So a loop can be used to repeat the same portion of code or a block of code a set number of times. But now there's a distinction between the for loop that is used to repeat the block of code really a fixed number of times. So if we know ahead of time how many times this block of code should be executed, typically we use a for loop. This is in opposition to the while loop that is used to repeat a certain task until some condition fails. But you see that here, we might not know ahead of time how many steps is it going to take for the condition to fail. So in which case, we need a while loop. Now, all of that, again, sounds a bit abstract, so this is an overview. Obviously, we're going to explain each of these and give examples to ground this in reality. Now, there's a last comment here. In an algorithm, logical operations are used to decide whether a loop should continue or not. Yes, although the topic of algorithms will be discussed in more detail in week 7, which probably will be the last week of our content. So let's begin with the if-else statement. So the general structure or syntax is this. Now, this is not executable code. It's just to show you the structure. If a certain condition is true, then do something. Now, if the condition is false, so else, if another condition is true, then you do this, you do something else. And then if both those conditions are false, then lastly, you will do otherwise. Okay, and again, this is just the general structure. So the order of operations from our perspective, well, this is what I just said, but let's repeat. I hear repetition is good for understanding. So what this is doing is checking if condition, the first one here, is true. And if that's true, the code will execute something and finish. So exit the code. So if this is true, do this, and then you don't even gonna read this. If condition is false, then we go to the else. And if condition 2 is true, then you execute something else, and again you finish. You don't even go here. And lastly, if both conditions are false, then you execute otherwise, and you finish. When I say you, well, it's the code who does that. Now, again, please take a moment to make sure you understand the general structure here, the logic of it. It is quite essential in programming. But to help you, we have an example here, a simple one. So let's see what this code does. First, we declare x to be equal to 3, y to be equal to 4. Now we have the first if. So if this condition, then see you have the curly brackets. So the first, this corresponds to something here. So execute this. So if x is smaller than y, so if this is true, print, well, this is printing to the console, just the sentence, x smaller than y. Else, meaning if this is not true, if this is true, if x equals y, then print x equals y. And then lastly, if this is false and this is false, so else do this, print x larger than y. And you see, if you execute this whole thing, the result will be, of course, x smaller than y, because in this specific example, well, x indeed is smaller than y. Now let me just show you that it works for any numbers and should give us the expected result in R. You can try for yourself as well. So I'm just going to go to our studio here. I'll put it in the, no, I don't want to put it in the console directly. I want to put it in my script. And then from the script, I'm going to execute this. Okay, it will give me the result. But then my point is just, if I put that x is actually bigger, I should get the correct result. Yes, x larger than y. And if they're the same, well, again, it should work. X equals y. Very good. Now here, there's two remarks. The first one is, you can use as many else if as you want. So here, we had an example where we only have one else if, but you can have many, many, many. Because, okay, here I suppose it's an example where there's really only 3 possibilities. But in general, you can have many, many, many different possibilities. So you could have, okay, if this is true, well, do this, but else do this. If that's not true, else if do this, else if do this. So the point here is just, you could have another else if after the first else if, and another else if, and so on. But again, the order matters in the sense that the code first checks the first condition, and if it's true, it just stops, right? It does whatever it is, and it doesn't check the rest of the code. But then it goes to the second and the third and so on. And at the very end, if everything fails, this is what is going to be executed. Okay, now the other comment here is that it is not strictly required to use else. You can get away with only ifs, but that is not efficient. Do you see why? Now, first, let me illustrate what I mean. So I'm gonna copy this code to RStudio. Now, if you don't want to use else, again, it's possible. You do need to be a bit careful with the syntax. So let's go in R and well, the code is already there. So actually, I'm gonna make a few mistakes here. So I told you, okay, I don't need else actually. So let's delete all the else and see what happened. And well, the last else I need to replace it with if, because I still want the code to check this condition. So let's try this. Now can you see ahead of time if this is gonna work? Let's try. No, this didn't work because I made a silly mistake. I replaced the last else with just if, but if what, right? I haven't put a condition, right? So I'm going to put the last condition, which would be if x bigger than y. Now, you read this, you probably expect it to work. I would expect it to work probably, but actually there's still a mistake. That's the way if works. So the if it doesn't come after else, it needs to be on a new line, right? So this curly bracket if R doesn't like that, so I need to put it there on a new line. And same thing with the last one. So here this should work really. So let's try. Okay, yes, I got my x equals y. And then let's try with another one. Okay, I get yes, x larger than y. And let's try the last possibility here. Okay, I got my x smaller than y here. But that's not really recommended. And can you to skip the else? Can you see why it's not really efficient? Well, it's because of what I said before. If you use only if, every single condition will be checked. Every single condition will be checked. And now in this simple example, it doesn't take much time to check three conditions, but in practice, it could matter that if the first one is true, well, that's it. You don't want all the others to be checked because you've already found the one that's true. You see what I mean? So the difference really is in efficiency. Um, Again, the point is if early in the code something is true, you want it to exit and not check the other ones because that takes computing power. Hope this point is relatively clear. Where again, here, even though exactly one is true, when I execute this, R is going to check, okay, is this true? If so, print. If this true, if so, print. Is this true? If so, print, whatever, right? So it's going to check all three. Okay, now we get to the for loop. So the general syntax will be for, so for is a keyword, item in vector. So, and then do something. Now, again, this is the general structure. What happens here is R will run do something for every item in the vector. So imagine that this is some vector. It can be 1, 2, 3, 4, 5 up to a certain number, but it doesn't have to be. It can be just a whatever vector of I believe numerical values. Although probably not. That can probably be any vector. But usually it's going to be a numerical vector. Now, so again, R will run do something for every element in the vector, and typically it will use each of those items in the vector to do something at each iteration. So let's review a simple example. We set a variable called total to be 0, and then for, so again, that's the keyword for, then open regular bracket x in, then this vector. You see, so this is looks like an arbitrary vector. In fact, it's the vector of, oh, sorry about that. Only the first few prime numbers. Now, curly brackets, careful, this needs to be a curly bracket. Total equals total plus x. So here, it's quite simple. At every step, every iteration, the total gets updated to add the next element in the vector. So you see, it's in fact a pretty inefficient way to add all the numbers in this vector. But this is for the purpose of illustration of what a for loops does. Oh, and here just to show you what happens at each step, or yeah, to show you that total, sorry, that x is being updated at each step of the for loop. We use print. So print is simply displaying the result in the console. So x will in turn take the values 3, 7, 11, 13, 17. Because we have print x, you see they are all displayed in turn. But the main thing that happens here is that the total is updated. So at the end, if you display total, well, it will have added all those numbers. Now again, this example is purely pedagogical to show you what a for loop does. In reality, if you want to add all those numbers, you would just use the function sum, right? So you would not use a loop. If you use a loop to do something simple like that, that's bad coding in R. Let me just show you what I mean. If you want to sum all those prime numbers, just do that. Okay, sum the vector is already efficiently doing what you want. You don't need a loop to do that. Okay, and then again, try to understand the general structure intuitively. So I'll just repeat. Sorry if I'm repeating myself a lot, but at every step, x is going to take in turn each of those values and do something with x. So you see, I could have done something more fancy with x, right? And more complicated calculations, but for a set number of iteration, well, yes, because I know here in this vector there's 5 operations, so it's going to do something 5 times, each time with a different value of x. And yeah, so that's the general idea of the for loop. Okay, here there's just a bit of a I suppose visualization or chart of what's happening here, but it's just telling you, okay, the set of scenarios, it's going to execute each of them, and then it's going to end, which is quite simple. Now we're going to see the while loop, which is a little bit different. But before, there is an exercise for you, very exciting. So you open a new bank account at time 0, you deposit 500. Now, for some reason, your account earns I% per year, but in year I. So 1% in the first year, 2% in the second year, and so on. So the question is, what would be your account balance at the end of 10 years? Now, I think conceptually you see what you need to do. 500 times 1%, then times 2%, then times 3% up to the 10th year. Again, this is an example where you don't really need a loop, but to practice what a loop does, can you do it with a for loop? Try to do it for yourself. While you do that, I'll take a sip in my Mr. Happy cup. Okay, so let's present the solution. It's very similar to the previous example. It's just that we have a multiplication instead of addition. So there's 10 years. So after I set my balance to 500, I can have a for loop that needs to run 10 times because I need to update balance 10 times. And here it's quite simple. The interest rate is just 1, 2, 3, 4, 5. So the vector I need is 1, 2, 3, 4, 5 up to 10. And then I can do something like this. Each time I update my balance to now be balance. So the old balance times 1 plus I%. So see, careful here that if I is 1, well, 1 plus I divided by 100 will be 1.01, which is what I need to multiply balance by to get my new balance at the end of the year for the first year. And then you see, maybe let me just explain this to be sure. I'm updating balance. So what this has the effect of doing is the old balance is multiplied by something, and then because I put it inside the object balance, it is updated. And again, I do that 10 times. So the last time will be, well, the balance in year 9 multiplied by 1.1 because it's a 10% interest rate, and then that's it. Then after the iteration for I equals 10 is done, the for loop is over, and I can display balance, and it will give me what I want. And again, you didn't need a loop for this. It's more for a pedagogical reason. You could have used, well, there's a function product. There's a function product. Let's see in real time if we can get the same thing with function product. Yeah, it should really work. So I'll just copy this. I'm just thinking in my mind. Yeah, this is gonna work. So if I type this, but instead of I'd put directly the vector. You see, this is going to create a vector of all the, what I would call accumulation factors, right? So here, the result in the console will be 1.01, 1.02, blah, blah, blah. So in fact, all I need to do is multiply all those numbers together and multiply by the initial balance should be giving the same result, right? So product, and here you can use the function product for this. Product of all those things times the initial balance, which was 500, will give me hopefully the same number. Yes, 850. So again, we show you the general syntax of a for loop, but very often you can get away without a for loop, which is usually considered better. Okay, back to my slides. Now we get to while. Maybe while is more useful in the sense that it's perhaps harder to replace with a syntax such as the one I've just presented. So anyway, let's present the while. The general syntax is simply while condition. So while the condition is true, do something. So it repeats whatever commands are inside the bracket as long as the condition is true. So let's present again a super simple example. So here I have my two numbers. While their sum is smaller than 6, do something, and the do something is very simple here. I'm updating x to be the old x plus y. Now, y is never updated, so in this example, y will always be equal to 1, okay? We never update y. And then print the result. So you see, first time, while this is true, so while x plus y is smaller than 6, do something. So the first time, obviously, this is going to be true because 3 is smaller than 6. Then x will be updated to 3. And then print. Now x is 3, 3 plus 1, print 4. I get my 4. Then while now the sum is 4, it's still smaller than 6, x gets updated again, and then print the sum, now the sum is 5. Then the last time is going to print x plus y, that is 6. Now this last time, x is in fact 5. So when it goes back and checks, while 5 plus 1 is smaller than 6, well, that's true. Sorry, that's not true anymore. That's not true anymore because it's a strictly smaller. So then the loop exits, and whatever is here is not executed. Okay, so again, the whatever's inside the while will be executed for as long as this statement is true. And yes, the last x, if you type x at the end of this thing, the last one is 5. Well, indeed, because again, the logic is when x is 5 and the loop checks 5 plus 1 smaller than 6, false. So it's not going to update. It's not going to enter the loop again. So it's not going to update x. X will never get to be 6. Okay, now this is just a summary of each iteration of the loop, what's happening. And the chart here is, you see, it's a bit more complex in the sense that we start with some initial statement, initial state of the world. In this case, x is 2 and y is 1. And then if the condition is satisfied, we execute the command again. So we execute whatever is here. But eventually, if the condition is not satisfied, so we go here false, and we exit the loop. Okay, exercise for you to practice the while loop. With the help of the function rpois, this generates, in this case, if you use n equals 1, it generates one random observation from the Poisson distribution with a lambda of 2. So generate a series of Poisson 2, so random variables, or realization of random variables, we should say x1, x2, x3, blah, 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 until one of them is equal to 5. Until one of them is equal to 5. So you see, a Poisson with a mean of 2, it's not that likely that it's going to be equal to 5, but eventually it would if you generate many, many of them. Now store those random variables and display the full sequence. Okay, so can you think of a way to do that using the while loop? Try to do it. Okay, now I'll present a possible solution. You first generate the very first observation. So again, I put inside X some random Poisson with the parameter lambda equals 2. Now, to start with, our sequence only contains the first result, X. And here the point is that I want the full sequence at the end. So I need to create a new object that is not only one random number, but it's the whole sequence. So here I call it x.vector. Now, while my x is not 5, careful here, while the x is not 5, then I need to do something. Then I need to keep growing the sequence. So while this is true, so while it's true that x is not 5, this means I need to keep going. So what I do is simple. I create a new x. So I careful that here, if x equals Poisson, it's going to erase the old x. But that's fine because the old x is already contained in the vector. So the new x will be a new Poisson. And again, those are randomly generated numbers, so they won't all be equal. And then I update my x vector, and I use the function just c. This is simply putting x as the last value in the vector, right? So I take my old vector, and I put to it the new value of x. So I just append to my x vector the new value of x. And that's it. You see, as long as I don't get x equals 5, this loop will continue. And and as soon as x equals 5, then the loop will stop. And so at the end, if I display my whole sequence, x vector, here it's relatively long. So it took many, many times before I get to the very last 5, and then my loop exits. Because again, the logic is this statement, x not equal to 5, if this is true, I keep going. But if this is false, and x not equal to 5 being false would mean that x actually equals to 5. In that case, this is not executed anymore, and we stop, which it looks like it worked because obviously if you look, the only 5 here is the very last one. Okay, just an aside on the curly brackets here. Hopefully this part of the slides has demonstrated the importance of the braces. Okay, yeah, but braces, I suppose, another name for curly brackets in writing your code. And not only does it visually organize your code, but it also tells R which parts of your code belong to what. And obviously the brackets are really needed. Like you cannot not have them. And if you have too many or too few of them, your code is just not going to run. So a common error you're going to encounter is something like this. Error in parse text, blah, blah, blah. For example, this code has a mistake in it. Do you spot it straight away? Maybe you do. Well, okay, this for loop is opened here. It looks to be closed here, so that's fine. If it's opened here, it's closed here. But then what is this doing? It's not doing anything, right? So this one shouldn't be there. Shouldn't be there. Okay, so here, this is something I already started to talk about, but in many other programming languages, loops are heavily used. But in R, really the standard advice is that you should generally avoid them when possible. So if you can do something without a loop, do that option. And now this is due to the inbuilt vectorization behavior of R that we'll cover in the next slide. Now here, I do need to put a bit of caveat to this. In newer versions of R, there is some debate in the R community about how bad loops are. And so here I linked to this post where they kind of show that, okay, it's really not that bad, at least for some of the examples they have here. Now, this is a bit, I suppose because it's a bit debated, I cannot give you like a strong recommendation, but I would just say the small example I showed you before that you basically can get away with a simple command like sum or product. There, yes, don't use a loop for those things. Like it's just inefficient. But in general, I don't think loops are as bad as some people might tell you. Okay, the last one is unrelated to the first two bullet points here. There's other control flow statements that I don't think we're going to use too much, but just for your information, you'll know they exist. Break. If you put a break in your code, it's just going to exit the code, right? So sometimes you just want that if something is true, just exit. And next is going to stop the current iteration and go to the next iteration. But again, maybe those are not as important as the others. So I'll let you read about them either in the book or at this link if you want to know more about break and next. But for now, we do need to talk about vectorization. And here, sorry that we seem to jump from American spelling to British spelling sometimes, but maybe then everybody feels included like that. But anyway, vectorization, I don't know if it's like clear-cut defined concept, but it just means that R really naturally operates and easily operates on vectors and matrices without needing loops, So here we put some examples to illustrate this. And those are things we've already seen, at least some of them. For those examples, we declare a vector X, a vector Y. Okay, and then, for example, X is a vector, but very easily you can add a set constant to every element of the vector. And of course, you don't need a loop for that. If you type X plus 5, it's just going to add 5 to every single element of this vector. So you don't need a loop to do that. You could do it with a loop, a for loop, like 1, 2, 3, 4, add 5 to each of those numbers, but would be very inefficient. And by inefficient here, I mean the syntax is cumbersome. It's longer to do it with a loop, but also most likely it's going to take longer to do it. Then what else? Well, not any functions, but many functions, they will compute something for every element of the vector, like one shot, right? So square root of X will give you the square root of every element of the vector. Again, you don't need a loop to do that. You just use the function square root. X plus Y, those are two vectors. If you add them together, it's going to element by element add 1 and 5, then 2 and 6, and so on. Again, no need for a loop. Then the other example has to do with a matrix, but similar behavior. If I create a matrix here, so it's a square matrix, 3 by 3 with just the numbers 1 through to 9. A function here, exponent of matrix, will just take e to the power of all the numbers in the matrix. So this is e to the power 1, or just e, and then e to the e to the power 2, e to the power 3, e to the power 4, and so on, e to the power 9. So again, I apply a function to my matrix, and then each of the elements gets the function applied to them without needing a loop. And lastly, sum of m. So sum of m very efficiently will sum all those numbers together and gives me one final result. 1 plus 2 plus blah, blah, up to 9. So we call this behavior vectorization, and it's one of the main strengths of R because it makes the syntax quite compact and elegant, if I can say so myself. And also, vectorization is usually quicker than loops. Now, much quicker can be, but there, as I said before, there's a bit of a caveat to that. I think newer versions of R are much better in terms of speed of loops. But now let's present an example where we actually have a timed, we time our code. So you can do that. There's quite a few functions that allow you to do that, but here, very simple. We generate a very large vector of random uniforms. Okay, so our unif generates this number, 100 million random uniforms, and we store them all in a vector called x. And then we just want to sum all those elements. Now, we do it in the inefficient manner of using a for loop. So for all the elements in the vector x, so from 1, 2, 3 up to n, and n again is this huge number, 100 million. What we do is we update z to be z plus the specific element of the vector x. So again, here we've written in one line, one shot, but convince yourself that this syntax is simply adding all the numbers in the vector x together. Yeah, it really is just adding all the numbers of x together. And you see, because we use this function system time, it times our code. So it's really a timer. And here we find that the total elapsed time is 1.25 seconds. So 1.25 seconds to add all those numbers together, 100 million of them. But if you do that with just the function sum, which again, really you should use for a task like that, it's much quicker. So it only took 0.08 seconds, which is many times smaller than this number. So here, yes, of course, we have confirmation that not only is a for loop a bit cumbersome in terms of notation, but it's much slower than the function sum. Now, a few more helpful functions. Now, as I said, many functions in R apply to all items of a given vector, and they also return a vector. So as we've just seen, square root, if you apply square root to a vector, well, it's going to find the square root of every single element in the vector. Many functions are like that, exp, log, and so on. Now, knowing and using those functions should make your life easier. Obviously, it's hard to know every single function in R, so it's, I suppose, as you do more R, you get to learn more of those functions and, discover more of those functions. Here we present two more. Before that, just a general comment that often you could get away without knowing those functions, right? So you could perform most tasks in a custom manner, either using vectorization or not. But the resulting syntax is often kind of clunky or cumbersome and not necessarily the faster. So the point is just knowing the shortcut functions that already exist usually simplifies your life. And here we give you an example to illustrate this. So from a given vector, let's say we want to double all even numbers in the vector and off all odd entries. So you have this vector here. We want to double every number that is even. So 2 should become a 4 and 4 should become an 8. And we want to off the odd one. So 1 should become 0.5 and 7 should become 3.5. Now, there's many ways to do this, at least three. You could use a loop. That's inefficient. We haven't even bothered to write it down. So, but you could for, and then you go through every element of the vector. For each of them, you check individually, is it even or odd, and then you do the replacement. Then you can do this without a loop by yourself coding some sort of vectorized command that will do this. We've done it here for you. It works. There's no problem with that. It's just maybe slightly ugly. Okay, y will be our final result, our final vector. So we start by putting all the x's into y, and then we change them. So okay, so here, okay, I suppose we use logical masks. So y percentage, this will give you the remainder of the division. So if the remainder of the division by 2 is equal to 0, well, you have an even number, right? Because, well, yeah, if any number divided by 2, if there's no remainder to the division, well, it has to be an even number. So that's the logic here. So this finds all the y's that are even. Now, the actual values of y that will be true here, those are the ones you should replace by 2 times those values. So if I, again, take those values specifically and multiply by 2, it should give me what I want. Again, this is a bit hard to follow, so if you're a bit confused, try it. Like, try it out, see what this does, and then see what this does. And convince yourself it is what we want. And here, the same thing. If the division by 2 has a reminder of 1, well, it means it's an odd number. And if it's an odd number, we should grab those numbers and multiply them by 0.5. You see here, we got what we wanted. The odd ones were divided by 2, and the even ones were multiplied by 2. But again, this is a bit cumbersome. So if you know the if-else function, then you will do this in a more neat notation. So if-else in general, I really think you should know it. So let's explain. Well, if-else. So if-else is checking a condition, but careful, for every element of a vector, and then doing something for each element of this vector. So in this specific case, remember x is a vector. So if the division by 2 of every element in the vector is 0, this indicates we have an even number, then we shall multiply that element in the vector by 2. Otherwise, we should multiply it by 0.5. So so in general, if else has 3 arguments, this is the condition. So the first one this is the condition. This is what we should return if the condition is true. So in this case, if a number is divisible by 2, meaning it's even, return twice the number. And then the last argument of if else is, what should we do if the condition is false, right? So if this is false, then do this. But again, the point of if else is that it's vectorized. It's going to check the condition for every element in the vector, and then it's going to do that for every element of the vector if the condition is true, and it's going to do that otherwise. I hope it's not too confusing, but I don't know how else I can explain. Let me just show you the syntax in R, what this does, right? In case you haven't checked yourself. So again, if I have x to be a vector of whatever, I don't remember the numbers in the other slides, but I'll just invent my own numbers. Okay, so that's a vector. And so here you see if the remainder of the division of x with 2 is 0, it means I have even number, right? So 3 is not even, so false. 4 is even, so true. 5 is odd, so false, and so on. I don't know if that helps, but then I mean, I can try this for the whole vector I just created. So you see, for every element, right? So here, the first one, if it's true, do this, but the very first is false, so it's going to do this instead. It's going to multiply the first element 3 by 0.5. So I'm going to get my 1.5. And for the second element of the vector, this statement is true. So of course it's going to do this operation. But careful, this operation applied to the second element of the vector. That's the key point, right? So the second element of the vector being 4. 4 times 2 is 8. Okay, I think that's enough explanations for this. Okay, one other function that could be useful for you, at some point at least, is Pmax. So Pmax finds the maximum between two sets of numbers. So it's going to find element, like comparing element by element, what is the maximum between two numbers. So let's review an example. Again, two numerical vectors. Now, my goal is to check for each pair of element, which is bigger, right? So is 2 bigger than 3? Is 5 bigger than 4? Is 7 bigger than 8? Now, there's a function called max, right? There's a function called max in R, but it doesn't apply. I mean, it applies to a vector, but it's not going to compare element by element two vectors. So max xy does not do what I want. Now, max xy will return 8. Well, yes, I think you can guess what max does. It just checks in those two vectors which is the largest observation, right? Which obviously it's 8. To do what I want, I use Pmax. So again, Pmax is going to check, okay, first element of the first vector compared to the first element of the second vector, which is the max. Well, obviously it's 3. And then it's going to compare 5 to 4, and so on. Now, for information, sometimes you just want to, you have a whole vector of numbers, but you want to compare all of them to just one number. But again, you want element by element comparison. So Pmax can be used for that as well. So if you compare the whole vector x to a single number, it's just going to compare, okay, between 2 and 6, what's the biggest? Of course, 6. Between 5 and 6, which one is the biggest? 6. And between, lastly, 7 and 6, obviously 7 wins because it's the biggest. Okay, so bottom line, using a loop in R, okay, certainly is not a crime. And sometimes you have to. But before you use a loop, ask yourself, is there an already existing function that can be used to do the task I want to do? A simple function like sum or product or whatever. Some of those we've covered here. If else, for example. Now, if there's not such a function, maybe I can still avoid a loop by using some customized syntax that exploits vectorization, like the one we've covered here. And lastly, if not, maybe I can create my own function to perform this task. What? Create my own function? Yes, yes, yes. But this will be the topic of the next video. For now, I'll stop here and say bye-bye.